Hi, everyone, and welcome back to the Regression and Beyond series. In this lab, I'm going to be expanding on the last one, multiple regression using ordinary least squares estimation. And this time, we're going to be adding in interaction. So again, the data file and this script file are linked below if you want to work through this yourself, or again, use this for your own purposes as a basis. Many of the same steps that we walked through last time. So first I'm loading Rio. Remember, this is just one way that you can get your data into R. And remember, you'll need to make a path specific to your computer to do this. Or again, there's several other ways to get your data, like importing the data set up here. So we imported it. I called mine data, again, to be simple. We have 500 observations and 4 variables. Let's do a basic check at descriptive statistics. Looks like they're mostly continuous variables. X3 looks like it's probably dichotomous, so pretty similar to last time. Again, I'm going to name this first model simply LM1, but you can name it whatever you would like. We're going to regress Y onto X1, X2, and X3 using the summary function to look at it. We see that they're all significantly related to Y. We're explaining almost 80% of the variance in Y, a pretty large amount of variance to explain. And now let's check the assumptions visually and statistically. So working through the process that we did last time. So first going to look at the normality of residuals assumption. Visually doesn't look too bad, some bit of a deviation, but doesn't look too bad there. Now I'm going to load ggplot and do a histogram of the residuals. Again, doesn't look great, but not too bad just visually. But let's do a check. Oh, forgot to load moments. All right, so if it was a perfectly normal distribution, skew would be 0 and kurtosis would be 3. So it does look slightly off. We're going to do the JB test. And in contrast to last time, in this case, it is significant if we have the alpha at 0.05. So we have to reject the null hypothesis that skew and excess kurtosis are equal to 0. So might not be able to hold that assumption. Now let's go to check on heteroscedasticity. And again, visually not looking super great. What we'd want to see is that red line to be completely horizontal. It is not doing that, so that is not initially a good sign for us, but let's do some testing on this. I'm not going to do the full generic white test like we did last time. Okay, so the white test is significant. Okay, so it looks like our assumptions are violated. Just want you to hold on to that thought for now, as we're going to kind of find out why indirectly here. In a typical case, if you ran into this situation, your assumptions violated, you might do something differently. But in this case, we're going to realize maybe why those assumptions are violated in that first model. So we're talking about interactions, right? So let's add in interaction. In this case, this is how we do that. The only difference, so a little asterisk or multiplication sign, x1 times x2. So we're just adding that one interaction. Again, I'm simple, so I'm just naming this LM2. Let's have a look. So some things pop out. X1 and X2 are no longer significant, though the interaction between them is significant. Looks like we have an increase in R squared. It is now about 0.83 with rounding. So we're explaining more variance when we added that interaction. Now I'm going to do something again that I showed before in the last video to calculate that R squared difference. So adding that interaction explains an additional 4% of the variance in Y. Now, not everyone does this, not necessarily required, but you can also do a formal test of this when you add an interaction to a model, or more broadly, if you're interested in comparing models. Specifically, they'd have to be nested, and we'll be talking more about that in future videos. But here we would have an instance of that, essentially a model with the interaction, model without the interaction. So here we can actually test them against each other, essentially testing, is that difference in R squared different? Is that statistically meaningful? And the command is quite simple. It's the ANOVA function. I'm going to be familiar with ANOVA. It's something commonly done for the omnibus model test in regression. And here we can use the very similar approach. Essentially, if you look here at what we're actually doing, basically we're looking at the difference in residual sum of squares. And then we have 1 degree of freedom difference between the models because it's the model with interaction versus model without. So that's a difference of 1. Then we get our F statistics. So it is significant. So in other words, we would conclude here that adding that interaction is statistically meaningful more broadly. So I have some additional kind of details about degrees of freedom in the notes there, but that's broadly what we would conclude at this point. It adds to our model to have that interaction. And now let's look at those assumptions again, but in the model with the interaction. So first, some visual inspection. Again, maybe looks a little bit better in terms of normality. Let's look at a histogram. Also, maybe a little bit better. Again, not perfect, rarely ever is. And we do the test. Okay, it's not significant. So more tenable to hold that normality assumption. Check out the variance. Again, we reach a similar conclusion that our assumptions are now more tenable. And now where I kind of want to end this video here, and in the next video, we'll pick up right where we left up here. But to quickly make a point about this, in the future, we're going to be covering some what are often called robust approaches that can be used when you have an assumption violation. But what we just worked through illustrates perhaps a more fundamental point, which is that we technically assume that we have the correct model specification or that our model is correct. And assumption violations can be an outcome of an incorrect model. So in this case, say I drew on some theory and didn't include the interactive effect there, and then I had assumption violations, right? One thing I might do is use an approach that I'll show you, quote unquote, kind of more a robust approach to try to address it, or essentially it's kind of, putting, I think, kind of a band-aid on, in this case, what we see is a more fundamental issue, which is maybe there is some really deeper meaning behind that interaction, and that was important to include. When we included it, now our assumptions were met or more tenable to assume. But when we failed to include it, we had assumption violations. So when you have assumption violations, and it's very common in future videos, we'll be using often robust approaches, which, as the name implies, are supposed to be kind of robust to things like assumption violations. But I think it's also important to think about it at a more fundamental level of really thinking about, is your model right? Or kind of ground one, what's your kind of theory and assumptions going into this that's informing your variables and the relationships between them in the model. So in the next video, we're going to pick up right here where we left off, and I hope to see you there. Thanks.